George. George works at Amkor. His presentation is Test Impact of Chiplets in Packages. George joined Amkor in 2020 and is currently responsible for global test services operations. Thank you, George. Please go ahead.
Thank you for that introduction. Hello, everyone, and thank you for attending. It's already been a very exciting conference so far, and I'm very excited and pleased to be able to discuss test as it relates to chiplets and the data that we get from that while the chiplets themselves continue to proliferate and grow in the market. Let's go here. I'm going to talk about a few things very quickly, and I'll spend more time near the end of the presentation to focus on some of the test and data and flows. But I'm just going to cover the chiplets and some of the end market impacts very quickly, talk a little bit about the different package technologies and landscapes. And I'm going to discuss some of the package applications and the aspects that we consider from a test perspective. And then the impact and opportunities for both test data, test flows. And I'll spend probably more time there at the end on test and the data and some of the methodologies there. Okay, let's get into it. The multi-die packages are everywhere. We're seeing customers coming from all end market applications: automotive, health and industrial, communications, artificial intelligence, networking, computing, and consumer. I mean, they're just coming everywhere. It's a big growth area for a lot of the OSATs, especially on the high-end packages, but it's coming from all market spaces. Let's talk about the technology integration processes. So when we have a system in package, a chiplet, and a module, we see 3D and interconnect technologies and wafer level technologies, both for fan in and fan out. So this is what the landscape looks like, both at IDMs and also in the OSAT world, where the higher densities for IOs, of course, are being driven by tighter and tighter IO pitches. And you can see for ultra high def fan out, quite a few players, 2.5D interposers, growing to 3D stacked memories, TSVs, micro bumps. I think Terrence talked a little bit about those today. Embedded silicon bridges and hybrid bonding and bumpless processing. So you can see that this is the landscape that we're facing as we improve IO densities and tighten IO pitches, which of course will impact our test capabilities. Really the point here is that the industry level is pushing in all segments. So we talked about the end markets, but it's really being seen in all segments: photonics, 5G RF, power management products, digital processors and memory, MEMS and sensors, analog and mixed signal products. So not only are we seeing these in all different end market, but we're also seeing that in different functional components in all those segments as well. So that's exciting for those of us that are working in this space. All right. Let's go through some of the technologies. Here at Amkor, we have three paths: RDL, interposer path, 3D stacking, and substrates that can be adapted to the specific requirements of that chiplet. You'll see some more of this as we go forward. If we talk about, I want to talk about some of the applications. So here's an application where we see molded and semi-molded packages, and we see multi-die packages. We see shielded multi-die packages, and you can see for this particular multi-die package where we have multiple types of passive components, wire bonded devices, pre-packaged IC, stacked die, and even compartmental shielding where necessary. in this particular, and this is an example of a highly integrated sensor product. If we look at the next application, so power. So there's quite a few different power packages. This is just a simple example of a single stack and a multiple stack QFN. In this particular case, inside that device, as we have multiple, it could be current regulators or voltage regulators all hooked up to a battery, we start seeing that this is the kind of integration, and how are we going to test these different parts inside a single chiplet in this case. Here's another example of a module that is built. We have a nice big power FET here with the controller embedded. So we'll talk some more about some of the test techniques for those. Here's another example of a system in package. We had in the past 2 modules that were built. And of course, the technology is being used to drive cost and area reduction. So in this case, we can see on this SIP where the memories now have been condensed, and we've achieved a significant area reduction of what these 2 modules used to be to this new chiplet SIP that we're building. That's one example. Let's talk about this one next, on a molded stack package, where we could have modem embedded, software defined radios embedded, the PMICs embedded, memories embedded. And in this case, where we would have an external or chip antenna, and you can see here under the logo Amkor, there's actually an antenna right underneath there. So that's another component that's being integrated into these multi-die chiplets that we're going to have to consider when it comes to test. That's an embedded patch antenna right there under the, under the Amkor logo. All right, where are we? All right, here's another example of packaging assembly that's enabling greater than 400 gigabits per second data rates. So this is our normal RX and TX path, but the point is here, this is just another area, another segment where chiplets are being utilized to enable very high data rates, optical silicon photonics. I think this is the final example I wanted to cover. High bandwidth memory. You can see the complexity here with stacking and substrate levels of processing. So quite a bit of complexity here on this particular device with the high bandwidth memory processing technology. Okay. The point is, as packaging complexities increase, our new matching test methodologies must be architected. All right, so we went through a bunch of cool pictures, both real and cartoons, and we start to see the challenges that we're going to face for observability and interrogating the part. Okay, let's look at some of the aspects that occur in our packaging assembly processes. So we might have overmolded or cavity packages, wire bond or flip chip, stacked die or side by side, material loop radius and gauge controls in the manufacturing process, molded in with EMI shielding, encapsulation, leaded or balled, different types of attached materials, laminates or lead frames. So these are all parts of the different assembly processing. And as test engineers, one, of course, we want to test go, no go. Is the product good? Can we ship it out? We also need to help the factory by debugging and identifying and helping the failure analysis to continuously improve those processes. Here, when we talk about test, we'll have some access, and we'll talk more about that as we go, but a test access port through a particular pin. This one is an example of where we'll physically make contact to this port, either for digital, power, analog sensing, or RF type testing. But there's also the case where we could have over-the-air testing as well. Okay, so these are the aspects in the manufacturing, some of the aspects in the manufacturing process. Let's talk about our production test challenges. So here we have our classical single die in a package that we're testing with production test equipment. Of course, we have our power supply, our pin electronics, our analog source and measurement instruments, and our RF source and measurement instruments. And so we have access to the die through the pins on the package, and we can test that die. But when we go to a chiplet, we may have access from production test to die number 1, and possibly through die 1 to die 2. There may be signal A that we do no longer, signal A on die 2 that we no longer have access to directly from the production test equipment. Or in case B, we have access from the test equipment directly to the die. So here's 3 different cases where we might have access or not have access directly from the production test equipment. So this starts the challenges that we're starting to face in observability with die beyond our immediate access through an external pin, or even through a radiative test. Okay. The industry's gotten together and put together this IEEE standard for test access architecture for 3-dimensional stacked integrated circuits. So what we see here is die 1. So as we were designing maybe this SoC, we would have a controller, a primary test access port controller that is visible from the external pins of the device. And then we might have secondary tap controllers that are accessing other physical blocks within that die. But what we're showing here is as we have die 2, 3, and 4, which we don't physically have access to externally at the external pins, we'll have to communicate and observe those die through those test ports, through the primary and secondary test ports. So that's a good example of the industry coming together to define the signals for 3-dimensional stacked integrated circuits to deal with those, let's call them hidden chips, those embedded chips within the chiplet. All right, let's talk about some other impacts to production test methodology. We've always had a functional and structural test content, built-in self-testing, structural-based final test. Nowadays, the equipment that we're using is starting to require significantly more protocol-aware instrumentation. So, the JTAG, PCI, SPI, even DDR interface, the equipment and the instrumentation, our requirements are starting to require much more protocol-aware instrumentation to be able to talk through those ports at that protocol to embedded die within the multi-chip module. We also have to worry and consider the concurrency with multi-site and within a single die. These are areas that the engineering teams are considering as they're selecting equipment and also designing the test solutions. Let's talk about system level production test. Historically, we've had functional tests and structural tests at the, in the wafer process, wafer test, also at the final test. Moving into the system and package in the chiplet space, system level test has become more and more critical. And you'll see that in a demonstration later on in the presentation, how we're moving a lot more of the test content from the system level application board into system level test once it's been packaged into the multi-chip module. Of course, we have to consider all the different interfaces that might be there, which is why we talked about the equipment needing to be more protocol aware than ever. Different test access ports and our contactless interfaces as well. So as we look and understand the challenges in front of us when it comes to the multi-chip modules and chiplets, the engineering teams need to consider the yield optimization and fault optimization, and Terrence talked about that quite a bit this morning. The quality and reliability, burn-in, and stress impacts as well. We'll talk about that in a couple slides. The thermal design of the solution. We can typically test and exercise the product far more than it will be in an application. Activating more gates, driving more current than it might even be an application for different reasons. Just for lower cost of test, so we can test the product quicker, and also for fault coverage. So the thermal design, of course, for those environments need to be considered by the team. And of course, we have a lot of content now at the system level test as we've integrated something that could be as simple as a component like a diode or a capacitor or inductor, along with an application processor, maybe a 5G RF, or a regulator, a voltage or current regulator, all at the system level test. So the test content is really quite significant now. So system level test today is offering us the ability to optimize our test coverage, and the teams will go and study how early can we capture something in the manufacturing flow, and where's our coverage, and how do all the parts finally work together at our system level test, and how can we balance the different temperatures that might be required along the flow for redundancy and ease of manufacturing processes. So that's it with system level production tests. I'm going to cover a couple more slides on this. Quite a bit of equipment. Our vendors in the industry have, we have a good selection of equipment. The things that are considered at system level tests when we talk about test equipment, of course, our normal power signal clock, and then the protocol aware that we talked about earlier. SLT requirements today have been becoming significantly eased by FPGA-based instrumentation and their popularity. So it enables the system test development engineer the ability to customize parts of the application to be tested, at the system level. Our handlers have a wide variety that we're seeing. Most of them have been massively parallel with high UPHs that can handle a very wide package size range on the handler side. On the test hardware, the requirements are to mimic the end application. with its increasing complexity, and the equipment needs to be scalable, so we're not, of course, we're able to reuse it over time. And of course, the increasing test coverage that we mentioned in the previous slide. What we're seeing in the industry from system level test equipment is equipments that are, hugely handler based, that have cavities in there that can be hooked up to very custom application boards and very custom solutions for system level test, to more expensive system level test equipment that has a lot of that capability built in for the application engineers to design their solution on the equipment. So that's what we're seeing as two general trends. Let's talk about, let's segue to the impacts to the test flow. We've talked about observability, we talked about digital test ports, a little bit about some of the methods that we can use, both physical and over-the-air testing. Let's talk about the impact to test flow. Here's an example of a single chip production test flow. We'll have we might have wafer probe and then go into packaging, and then we'll have some final test, and we might have a burn-in and then a second final test or a QA test. And then we might go into SLT and then a post test for our tray or tube or how we're going to ship the devices out. So this might be an example of a production test flow today with the different test insertions that we usually talk about. Let's talk about a potentially optimized high-level production test flow. So we might have a KGD wafer that we're trying to develop and ship to heterogeneous integrated packaging. We might have multiple products that are getting wafer probe now. Some of those products might have wafer level burn-in and stress in there. Once they go into the heterogeneous integrated packaging, the chiplets, we might be able to go directly into an SLT, where we can do the wide variety of test content that we talked about before. And in this loop, from an optimization perspective, we might have some kind of a sample burn-in or even a destructive burn-in here that feeds back into the wafer level burn-in and stress. And that was some of the feedback data that Ken talked about and Sergio talked a little bit about. And we're going to talk about a little bit of that more as well. So let's say here that we've done a significant level of test content. We've even done some wafer level burn-in and stress. We've gone into our packaging for our integrated devices, and we think that we have a good coverage level for system level test, and we get a test result. We can then pass that, and I think Dale Omar was talking about this earlier, the assumption being that production test is really just to decide go no go if the device is good enough to go out. So we might pass the device and go off to post test. But in today's high complex multi-chip modules, we have a couple of scenarios that might be occurring here to optimize our production test. We may take a sample of a good or even a sample of failing die. Let's say we take a sample of failing die and we send it into an additional test. This might be a final test with an ATE, not necessarily the SLT, where we can then take the information there for failure and yield optimization, and also from an OCAP perspective, where we are looking for anything that might be out of control. And then based on those results of this, let's say failing device samples, we'll make lot accept decisions. This is some of the things that Sergio was talking about, our lot accept based on our models. And then our production lot might be holding and waiting for this information to funnel through to give the green light to ship all of the units that pass, or maybe even a subset of them, or maybe none at all. Another example of a cost optimized production flow would be getting a test result, pulling a sample of good die, and sending those good die through some additional characterization from an ATE, or also maybe even some stress testing. Maybe those die will go through an additional burn-in. Maybe those devices will go through a Haas test. Maybe they'll go through a wire bond pull test. Based on those destructive tests on a sample, we can call that maybe ongoing reliability test, or at some frequency. That could be by assembly lot. It could be once a day per equipment. Then it goes into a lot accept situation, decision made, and then the material that's waiting at post-test can ship out for the next step in the manufacturing flow. So here, especially with system level tests, we have some opportunity for an optimized high-level production test flow that looks something like this. Okay, let's go to the next slide. We can see altered test flow. Our test content can be redistributed, and we have platform level test solutions at the SLT. Okay. And from Terrence, this is where if we get some SLT based results, we can use the sample basis to get some additional debug capability either on a sample basis. If we're not getting that, or we don't want to spend the time to get that, the SLT test. Okay. Let's talk about test data enabled advanced manufacturing. So today we will be sending, this is an example of sending the chips away from, out of your assembly and test factory into the module OEM integrator, where we might have these particular 6 devices now on the application board at the EMS. This is an example, of course, of a non-integrated application board. As we move forward, we might have now a multi-die package for devices 1, 2, 3, 4, and 5. And then device 6 may have gone through the manufacturing process on its merry way and got integrated again at the application board, pick and placed, put on the application board at the module integrator. So let's call that an example of an integrated solution at the application board. Okay, so if we keep these 2 scenarios in mind, the traditional non-integrated application board and the integrated application board, let's look at how test data would need to be enabled for advanced manufacturing. All right, here is a map of the non-integrated flow. We might have 6 different chips coming from 6 different vendors. And as they go through, they might have far different test flows. So for wafer 1, it might get a wafer test, but no bump, no additional wafer test, no post-bump wafer test. It might get an optical inspection. It might get packaged. It might have final test, and it might go right out the door. Wafer number 2 might go through a bump, then get a wafer test, then go through packaging, then have final test, burn-in, final test 2, and SLT. Very comprehensive flow. Similarly, you can see differences in the other chips that will eventually be integrated here at the EMS. So when it goes into the PCB assembly phase at the EMS, all of these chips are of course, pick and place, and then going through some level of system level tests, and even have flying probe capabilities as well, and some optical inspection. Today, most of these insertions have their own databases at the respective factories that they exist. And Sergio talked a lot about the need for sharing that data all across the supply chain for working models to improve performance and improving yields. Here, critical area is the electrical and physical traceability, not just for the wafers themselves, but also the carriers that are going on, or the chips themselves, but also the carriers that they're going into. Much of our equipment is able to read a barcode scanner or an RFID or something with, or even an optical picture of the wafer, reading the scribe, and even individually symbolized internally to the chip itself. For example, we might have a laser diode that's coming through one of these processes, because laser diodes are simply a diode. They have, zero embedded memory of any kind, and so there might be a physical die ID that is printed on the chip as it goes through the manufacturing process. So all of these different kinds of chips through all of this equipment, today we're needing the electrical and physical traceability, so our data analysts and our data engineers can aggregate that data all along the supply chain. So that's what's occurring today in a non-integrated solution. As we discussed a little bit about feeding back, here we might be taking discrete information at final test 1 for this chip, or maybe at skipping that and taking it at final test 2 for this chip, and feeding that back. And that's pretty obvious about feeding that back into the previous manufacturing steps to improve distributions and control quality, yield, and reliability. There's also the growing case where that information needs to be fed forward. Say for the example of a laser diode. The distributions of a laser diode will definitely have variance, as almost everything does. And it may not and will not have any onboard capability to trim that device. So as it's characterized going through the manufacturing flow from all the tests, that information today can be fed forward to the SLT at the EMS, where it can tell the associated driver what conditions to run that particular individual diode. And that's just one example. It could be any chip that doesn't have any onboard memory. So you can see now, if we only have physical traceability, we'd have to merge that with our electrical data and even our optical data if it's an optical product, and feed it forward so that the system board itself doesn't have to do all of that cross temperature, cross voltage, cross current, cross power, cross process tuning and incur that cost at the SLT phase at the EMS. And it may not even have visibility into that chip once it's embedded there. So that data can be fed forward as long as we have electrical and physical traceability to program the surrounding chips to tighten those distributions. Of course, if we tighten those distributions electrically and at the system level, then we can have probably higher yields as the products go through. and manufacture with maybe simpler processes at lower cost. That's the non-integrated case. So again, electrical and physical traceability for all the equipment involved and all the ICs as they come through, very, very important. It's also important for checking. So is that particular device appropriate rules checkers to be embedded here at this time? How can I have two diodes or two converters that have the exact same die ID? That's not possible. Something is wrong in the manufacturing process. We should run that checker on our data that we're feeding forward, halt the process, and see what's going on in that anomalous event. Okay, let's step to chiplets. Once we now have the case that I showed in the previous slide where the chips 1 through 5 have been integrated into a multi-die chiplet, while device number 6 is still going through independently through the process and eventually gets put together at the PCB assembly phase of the EMS. So now we can see that the processing steps for those die are going to be seeing quite a bit of the same environmental insertion. So what we were previously doing at the PCB EMS assembly stage has now been pushed to the left earlier in the manufacturing flow, of course. So now the test data that we're taking here will have the additional challenges that we mentioned before: observability, trying to get to internal chips that are not connected physically to external pins here at the embedded package. Now, how is the manufacturing flow and the data that we take going to change from here? As we stream the data out from here, and as we decide what those insertions are going to be, of course, that will need to be collected in our test database. And again, we're now feeding back to the manufacturing stages where tuning of the devices, both electronically or even physically in the fab, will need to occur. So here at the aggregated multi-die packaging phase, we're now collecting data that used to be collected here at the SLT. So we now have the opportunity as engineers in the supply chain to feed that data forward, especially from system level test, and modify and impact the content that will be happening at the SLT, the system level test at the EMS site. Some key points here are the processing and transmit infrastructure and architecture. So Ken showed you an example of the inference processing box that would be normally, I think, placed either at the very close to the test cell. We've talked about it directly with Adventest as well. How this test database architecture is designed can be very critical. We have several places where the data collection and the processing of that data, right? Sergio talked quite a bit about the modeling of and the processing that will need to occur both for electrical and optical data. So where is that going to occur? We have the first choice might be on the equipment. Most of the test equipment we have comes along with processing power of some kind. However, depending on the complexity of that processing power, if we were to use the tester processors, and that might be a DSP, or it might be a CPU, then we might bog down the test and cost us to have slower test time, and that's not an optimal situation. So that where the processing can or should occur needs to be understood by the test engineer and the IT engineers as they are crafting the test solution to optimize that manufacturing. Okay, so let's say that we decided we weren't going to do it on the equipment. We had to stream that data off. The next opportunity is what we call at the equipment, and that's the solution that Ken was talking about a little bit, where you put an additional compute box very close to the equipment and take the processing off of the original processors that might be on that test equipment. Because choices start having to be made. What is the optimal processing power that's needed? Should that processing power be a CPU? Should that processing power be a DSP? Should that processing power be a GPU? Especially when we have a bunch of physical traceability and we start having cameras embedded both in our wafer probers as well in some of our final test and equipment. What kind of processor do you need, and can you do it at the equipment? Is that the most optimum? Are you interacting directly with a single die, or are you waiting for the entire lot or wafer to be completed before decisions are made? That part of the architecture, the engineers are challenged to understand. If you're taking a significant amount of data, you can stream it off to this piece of equipment. Can you process that in a timely manner, either for the chip by chip or the wafer by wafer, the lot by lot basis, to impact and not slow down the indexing time or the test time of the lot? What we call is at the edge. There's another case where some of that data can be streamed directly off of the tester to the edge. And some part of the compute will occur at what we call the edge. Then there's the data center piece. How much of the data should go all the way back to the data center piece? What's that architecture going to look like? Where we have probably far more capacity, both from RAM, storage, and processing power to crunch that data and feed back the information necessary to either the manufacturing process or directly to the test cell or a follow-on test. For example, if we were taking test conditions at a wafer test to optimize the power of a particular product and trim it in, how are we feeding those conditions forward in order to optimize a different temperature for a final test that may have been tested at wafer test? So you can see now, because I think I've talked at length at the different decision points and attributes that need to be considered when we're designing the compute architecture, at the equipment, next to the equipment, at the edge, or back to the data center, and then even from the on-prem data center to an off-prem data center if we're aggregating multiple factories. And then the need to, feed back, feed forward, and adaptively change conditions within an insertion or from insertions to insertion.
George, George, we're running quite a bit over at the moment. Would you mind sort of wrapping up?
Yep, sure.
Thank you. Yeah.
So that's example of a non-integrated and then the integrated approach. We're pushing everything to the left. So Amkor has quite a bit of global test services, 24/7 test floors, many testers around the world at 7 locations, and we just announced our new location that we're building in Vietnam for production in 2023. We have test development services for all of the things that we just discussed, and of course we have testing for almost all commercial, industrial, automotive, discrete power, SIPs, and full end-of-the-line processing. In summary, our dielet chiplet integration allows for scaling in the future. But with those complexities, our business continues to have cost and performance challenges. So our call to action is both our advanced test methodologies and the data processing and storage and feed forward and feedback methods. Of course, is an industry leader in advanced packaging and production test solution. So thank you for your time today.
Thank you much, George, for that. We did run quite long. We do have 4 questions here. If we could just, I'll read the questions quick. They're all fairly brief. And if we could just sort of do a quick 1-sentence answer, George, please, I think that would be good. Then we can move on to the last present. First one is from Jan Wademan. With the increase in complexity, do you anticipate the need for X-ray inspection to detect potential failures in solder joints?
Yes, I do. So for X-ray inspection, that was when I was talking about optical, the X-ray itself will of course feed us back the optical image, which we can then do some pattern recognition methodologies on that and feed that forward or feed that back or make go no-go decisions. It can be done. Typically, that might be done at in a sample basis. So yes, I do see that as we move forward.
Okay. The next question is from Dale Omart. Can you define high UPH in the context of SLT? What is high?
A lot of it has to do with parallelism, maybe 500 or 1,000 devices in parallel. And then from a test time perspective, our system level test might be down in the 17-second range. So I haven't done the math from there to get the actual UPH, but I'm sure if I know Dale, he's probably got his calculator out and he's doing that right now. So
thank you. And another question from Derek Johnson. Which parameters do you track to check for assembly-related abnormalities?
There's quite a bit. So from a test perspective, we'll see the test signature. Then what is the fishbone diagram to trace that back to the particular processing that might occur. So we do opens and shorts testing on the substrates and lead frames incoming. So that's something we track to see, do we have a lot that might have significantly higher failure rate than another one before we even assemble the part? And how is that translating forward to our devices? So our wire thicknesses and content and die shear and die pull, those are things that we also monitor and can feed forward to decide if a lot can move forward or not. Another example is something maybe we call ongoing reliability test or wafer acceptance testing. So there might be some environmental testing. I think I mentioned it previously, like a HOST test that might be done as we go through. We don't necessarily wait for that. We might start processing because it doesn't fail very often. And then those two things are happening concurrently. And then we get an answer at the end that says everyone's passed and we can ship forward. So those are just a couple examples.
Thanks very much, George.
I'd like to thank all the presenters who presented today, and I also want to give an extra special thank you to all the sponsors who made this event possible. Our diamond sponsor is Amkor, with differentiators in technology, quality, and service. Our emerald sponsors are Adventest rated #1 in the VLSI research for ATE survey. Synopsis from Silicon to Software. And our Ruby sponsor, Tech Search International. So I'd like to thank all of them once again for making this event possible. I'd like to thank all of you for attending and look forward to seeing everybody here back again tomorrow. So thank you and have a good rest of your day.